Good morning, everyone.
Good morning.
How is everyone doing today? Did you have a nice weekend? Well relaxed, all that good stuff?
I did. Did you have a good weekend?
I did pretty good. Yesterday was my wife's birthday. We didn't have both our daughters, so we didn't do much celebrating, but at least I got to take her out and buy her some stuff she wanted, so that was nice. And I got to do some reading. I got to do some work around the house. I indentured some children to come pull weeds and play with the snakes in my flower beds. Uh, they were like 5 minutes into it, and this kid's like, "Look, I got a worm!" And he pulled it out, and it was a dang snake hibernating under the ground.
Oh my God. Oh, that's terrible.
But little kids, when they're that young, he was only like 9, so he's like, "Ah, it's a snake!"
My goodness.
So, anyways, it was just a garter snake, or at least that's what I could tell. It had that classic stripe down its back, but of course, covered in dirt, it's hard to tell colors.
Right.
And they're intimidating because they have that little band that comes out from their neck where their head meets and goes like that. And that's sort of the hallmark of a poisonous snake too, but it's not like I said, and they act really aggressive, so that's also another scary point about a garter snake. But anyways, I made about 6 or 7 videos this weekend, so life's going pretty good. Well, we've got a whopping 7 students in here. I'm feeling pretty good about the whole situation. We're doing chapter 21 today, which is pretty cool. This is when we start to talk about the Big Bang. So I'm pretty excited about covering that material. And I guess we'll get started. If I'm able to finish the chapter today, then I'm going to give you the afternoon off for lab, because I think the last lab was plenty of work for you to span 2 weeks, since you're supposed to be doing the constellations that I told you about. There were several constellations you're supposed to be looking at and doing research on. So I'm giving you today's lab time for more of that. I will send an email out to everyone if we get finished at class, just because there's some people in lab that might not be in lecture. So the test, remember, is due tomorrow night at 11:59 p.m. I'm probably tomorrow or Wednesday, I'm going to open up the next test, which will be due probably Sunday night. So that next one will be on 19 and 20. This one's on 17 and 18. There's more than one practice test out there, so be careful. Don't accidentally practice for the wrong test and then take the correct test, because that would be bad. Okay? So make sure you folks don't do that. Anyone have any questions before we get cracking?
No, I don't think so.
All right. Well, I just got another flux of 4 people coming in. 3, actually. So I just want to let everybody know the judges came in. We have a test that's due tomorrow at midnight. I will probably open either tomorrow, but definitely by Wednesday, I will open up your next test, which covers 19 and 20. And that's going to be due by Sunday. So make sure you get that done. Also, I warned them that there's multiple practice tests out there, so don't accidentally practice for the wrong test and then take the correct test, because you'll end up doing worse or doing badly. So that's not a good thing. I lost my video on the electromagnetic spectrum. I had a link to it in this course, but come to find out it was in my studio, and they just sent us a mean email wanting us to get rid of our studio files, and I thought I had recorded that one, but I had not, so I ended up throwing it away. So I got to make another one of those. So that's why you're seeing a lot of videos go up on my YouTube channel. Hopefully we'll get a lot more over the next several days, but I'm going to go ahead and get started on covering chapter 21, which is called The Big Bang. The Expanding Universe is what it's called, and it's about the Big Bang and Hubble and all that good stuff. So let's go ahead and get started. Again, anybody have any questions before we get started? I already asked that, but just in case. Okay, so it looks like we're good to go. So I'm going to share screen. This is, in fact, this is the PowerPoint that we'll be using for this chapter 21. I want to read over the objectives for chapter 21, so you'll know what our goal is, and be thinking of these perhaps in question form, so that you can try to think about writing essays on each of the 4 learning goals, those are really the holy grail of understanding everything. If you can write really robust, well explained, well supported by fact and evidence essays to answer each of the learning goals in a question form, then you probably have a good understanding of the chapter. So always go for that. That's why I also made it where you can write such an essay for reflection questions, since I don't have reflection questions on all the chapters yet. So here we go, the expanding universe. By the end of this chapter, you should be able to explain in detail the cosmological principle. I've hinted at that before, but that's sort of the fundamental continuance of the well, I shouldn't say Galileo's, but I should say the Copernican revolution, which is that, you know, in some sense, we're not special. So this is a continuance of that. Learning goal 2 is describe how the Hubble constant can be used to estimate the age of the universe. Learning goal 3, describe the observational evidence for the Big Bang. And then finally, learning goal 4, explain which chemical elements were created in the early hot universe. Okay, so those are the learning goals. Let's go for it now. So this picture right here, if you remember in the video, Beyond the Big Bang, or the Big Bang and Beyond, or whatever that was, the season 1 season finale of the Universe series. This was referred to as a speckled robin's egg. Now, I think it's a pretty apt description of its image, but it's basically an all-sky view of the cosmic microwave background radiation. And the deepest, darkest color of orange can be considered like the hottest portion, and the deepest, darkest color of blue can be considered the coldest portion. And what's remarkable about this isn't that it varies, but rather that it varies so little, because in fact the temperature differences are like in the 9th decimal place or some god awfully small amount like that. So it's really amazing that the cosmic microwave background radiation is so uniform. So that was a big question after the Big Bang, but that's what this figure is about. And they're asking, what is the evidence for the Big Bang? So let's get started. So cosmology is a study of the universe, including the structure, how it was made, how it's arranged, all that good stuff. It also covers the history. In other words, we want to know not only how stars live and die, but we want to know how they were created, how galaxies were created, how the galactic structures were formed. They want to know what are the origins of stars. Did stars come first and then there were galaxies? I know that sounds kind of weird because a galaxy is a collection of stars, but was there a clumping of gas such that, you know, hundreds of millions of stars came into being already in some structure that was built like a galaxy, or were individual stars sucked in to some gravitational center by other stars to make a galaxy? Those kind of questions. What were the conditions at the early times of the universe, and what's the end of our universe? Those are all what cosmology studies. And in fact, I often tell my students, cosmology is the area of physics where you study such a large scale that individual galaxies are considered point objects, point particles. In other words, we pretend like galaxies have no size whatsoever because an individual galaxy is so irrelevant to the bigger picture, but the sum of all the galaxies is quite important. So that's pretty mind-bending to think that cosmology studies the universe at a scale where galaxies, which are 100,000s of light years across, are pinpoints. So now the cosmological principle is something we apply. And like I said, I consider it a continuance of the Copernican revolution. It's basically just making the argument that there's no one spot in space or no one direction in space that's better than any other or even different than any other. So when, you know, we discovered, for instance, that we are but a third rock from the sun, and not even the most quote unquote impressive rock. I mean, we are in the sense that we have life, we have liquid water, we have an atmosphere, but, you know, there's other planets with with atmospheres, there's other planets with liquid water, there's other star systems with rocks orbiting it as well. So that by discovering that idea, then we put ourselves as on equal footing with a bunch of other inanimate objects, or at least our inanimate objects, the planets, the solar system, were put on an equal footing. I also suggested that, for instance, those t-shirts with pictures of like a big spiral galaxy, and it has this dot and it has an arrow pointing to it and it says "you are here." That's a continuous of the Copernican revolution. It's like we're this itty bitty speck in this huge thing. And then in biology, of course, the idea of the tree of life, that we all have one common ancestor, puts us as all separate leaves. Every bit of life on the planet is a separate, say, leaf or seed of a leaf, or seed of a flower, I should say, from the tree of life, and that every other piece of life existing today has a common ancestor, so that we're all in some sense cousins. That is a continuous of the Copernican revolution. And to put it more mathematically, we say the cosmological principle, which basically says the universe is the same everywhere and it's the same in all directions. Same everywhere means that it's homogeneous, and that homo means like, and genius in this case is more or less like formed, or like, I would assume that's what it means. But basically, homogeneous just means if you take any section of the universe big enough that you get a sample of every type thing that could be in the universe, and you compare it to another equally large section, then they will be about the same density, the same mass, the same temperature, all that good stuff. Also, if you look in any particular direction, let's say due east parallel to our horizon, right? If I look in that direction and I count 4,200 galaxies in one arc second area, then if I look any other random direction, I should see about 4,200 galaxies in one arc second. That's what isotropic means. So isotropic is the same in all directions. Homogeneous is the same in all locations. We've had many confirmations in some sense of the cosmological principle, but like all theories, which this is even a principle right now, we really are considering it more or less a theory because it's been tested numerous times and never failed. But like all theories, it only takes one experiment to prove us wrong. I mean, literally the universe that we can see, this isn't the whole universe, just the universe that we can see, is called the observable universe. And that is a sphere centered on us, whose radius, as best we can tell, is about 13.8 billion light years. But, there's a lot more universe beyond that. And we're probably maybe even a small fraction of the total universe. But what we've seen so far is that the cosmological principle is obeyed by space and the universe. So we have a lot of evidence confirming that the laws of physics are no different. Whoa, Nelly, whoa. Or no, ooh, I really finished that quickly. And class is over. No, just playing. So we finished that really quickly. That was terrible. So the laws of physics really are the same no matter where you're at. And that's the main thing we're trying to point out here with the cosmological principle, is by the universe being the same, we don't expect the matter to be any different. It's homogeneous and isotropic, but we also, in a more bigger way, do not expect the laws of physics to be different. So when we do chemistry here on Earth, we should be able to find the same sort of chemistry in other parts of the universe under the same conditions. So if we have to do chemistry at high temperature or low temperature, or physics at high temperature or low temperature, if we find an area of high temperature or low temperature, we should be able to show those things happening in other places in the universe. Again, the cosmological principle is only true on very large scales. For instance, if you take our solar system, then you'd reach the conclusion that the universe is not homogeneous, because you take another section about the size of the solar system, but let's say 1 light year from the solar system, you're not going to find matter nearly like what we have in our solar system. So you really have to take a large scale. So I like to use the idea of make sure you have at least, several of each objects that exist. For instance, we know black holes, white dwarfs, neutron stars, galaxies. We know all those things exist. We know spiral galaxies exist, elliptical galaxies exist, irregular galaxies exist, all that stuff. So if you find one area that has at least several of those things, then that area likely is big enough to compare to another area, as long as that area is big enough when we go to talk about homogeneity. Okay. All right, so that's me just going a little further into discussion about it than the book really shows, but I wanted you to think a little bit about what cosmological principle means, specifically in the idea of homogeneity. These photos are really good. So if we look at a universe as homogeneous, we could take off some area like here and say these are galaxies, these little dots. If we take this area right here, that's pretty good size. You see there's, dozens of galaxies there. So chances are you probably have many of each type, as well as all the different types of stars and post-star deaths and all that stuff in there. In fact, maybe it might be better to take about 100 or 1,000 galaxies. Now, if you compare that to any other area with 100 or 1,000 galaxies, you'd find that the conditions and the mass and density and all that stuff's about the same for two of those. But if the universe is not homogeneous, you might come over here and choose a section about as big as the one we just chose, and then find over on this half of space that that's not true at all. In fact, this area doesn't have nearly as much matter as that. So this isn't allowed by homogeneity. Similarly, if you look this direction, you choose this big area, you say, oh, that's good. If you look back this area, you're going to say, oh, that's good. But if you go just a little bit further, say this area, you get nothing, because in this case, basically we oriented all the matter along lines. So here's a row of matter, here's a row of matter, space again, here's a row of matter. This is an example of a non-isotropic universe. So those are really not homogeneous and not isotropic. If you want to find something that's homogeneous but not isotropic, then you look at this figure. So you can say it sees motion along this direction, right? And the matter is actually filled out sort of like this was. If you take off any big area big enough, all the matter in one area of equal size is going to be about the same as the other. But in this case, it's not isotropic because all the matter appears to be moving up or down in this particular frame, whereas nothing's moving left and right. That's another example that's not isotropic, but is homogeneous. So it's found that the universe, the entire universe at that matter, is expanding. And this is not something that was, sent to us from the depths of hell, as Louis Gohmert would suggest. This is actually something quite real. It was not only somewhat predicted by Alexander Friedman in Russia upon analyzing Einstein's theory of general relativity. Oddly enough, Einstein sort of found the same thing as well when he discovered his general theory of relativity and published it in 1915. But because we had no universe, or excuse me, we had no data showing that the universe was expanding, everything looked like a nice static universe. And Einstein particularly favored a static universe. He thought the universe looked exactly the way it does now and always has. Because of that, he basically put in something called the cosmological constant. And that sort of forced the universe to not be expanding or contracting. And in his case, he was more dealing with keeping it from expanding pretty much, or actually you could say he was keeping it from contracting, because the amount of matter they found, he realized that matter should be pulling all the other matter together, even weakly. But he put this cosmological constant in there, and that fixed the universe as static. Later, he said it was his largest blunder. He also said that he was so hard on experts for so long that God finally got him back by making him one, so that he screwed up as well. But as I said, Alexander Friedman took Einstein's equations and more or less predicted that the universe used to be smaller and is expanding. He was in Russia in the 1920s, which wasn't the best time to be in Russia to try to find out stuff or to get your observations discovered. So later on, I want to say in the 1918, 1920 area, roughly, a guy by the name of, dang it, I just lost his name. LeMaitre, George LeMaitre, or Georges LeMaitre. He was a Jesuit priest, and in fact, he had discovered using Einstein's equations that the universe was expanding. He sent his stuff to Einstein, as you saw in the video, and Einstein said your math is correct, but your physics is abominable, meaning that Einstein believed in a static universe, and this was showing clearly not that. Well, 1929, Edwin Hubble uses Henrietta Swan Leavitt's observation that stars that are variable, whose brightness varies with time, have a distinct relationship between the period of the oscillation of their brightness and their total luminosity. And once you have the luminosity of a star as opposed to the brightness, then you can use that to find distance. So Hubble in 1929 published his work, but he had basically taken and looked at the nebulas in our sky, one of which was called the Andromeda Nebula. And from that, he discovered that the Andromeda Nebula was in fact way too far away from us to be part of our galaxy, and in fact was its own island of stars. And that is literally the time where we finally realized that there are galaxies in our universe. Okay. We sort of just thought there was a hodgepodge of stars sort of centered on us. But in 1929, Hubble published that Andromeda was in fact a galaxy, and it was moving, in this case, it actually moved towards us because it's part of our local groups of gravity is pulling them all together. But he also did the same process with several other galaxies. And when he did, he found out that when you go twice as far away, the galaxies are moving away from us twice as fast. And when you go 3 times as far away, they're moving away from us 3 times as fast, and 4 times as far away, 4 times as fast. That became the Hubble's law. And you can't explain that except by assuming that the universe used to be really, really small. In fact, all the matter and everything used to be all in, say, at one day, it would be in an area about the size of our solar system one day after the Big Bang. And at 1/50th of a second after the Big Bang, it would all be in a size of space that was comparable to the size of our Earth. So you can trace all that back and see in time how long ago the entire universe would be in such small spaces. And that was the only way you could interpret that data. So it's not only consistent with what Alexander Friedman and LeMaitre had predicted, but it also was thrust upon us, not by those publications, because there was this horrible twist of fate that LeMaitre and other people like Gamow and Ralph Alpher and Herman didn't get their due when doing this. So, or when making these observations or these discoveries / predictions. So ultimately, we were faced with the idea of a Big Bang. And if you're thinking of the Big Bang as, let me stop this this sharing view for a second, and let me talk to you face to face. So if you're thinking of the Big Bang as the universe is just empty, and then all of a sudden in one particular location in space, there's an explosion, and out of that itty bitty spot exploded all the matter and energy that you see before us now. That is the common interpretation of what the Big Bang is, and it's completely wrong. Horribly wrong. All wrong. Okay. The space itself that we sort of predict like was always here and empty, that was created in the Big Bang. So the universe created not only all the matter and energy, it created the space itself. That's why we talk about the universe being all the matter, all the energy, all the dark matter, all the dark energy, and the space itself. Because we need you to understand that the Big Bang created the universe means that the space was created as well. And we don't think that that space is embedded in some higher space. So we're predicting a 4-dimensional space, taking the idea of relativity, a 4-dimensional space, X, Y, in, out would be, or excuse me, X axis is left, right, in, out might be Y axis, and up, down might be Z axis. There's 3 dimensions, and then time is the 4th one. That's our universe. That's what it's made up of. But that is what was created as well by the Big Bang. And that is, in some sense, this structure that's 4-dimensional, but we don't think it's 4-dimensional floating, say, inside of any other higher dimensional thing or anything like that. We just don't know. Okay. But we don't need it to be. We just understand that the universe was created in an instant. It wasn't big. It started off, as I told you, 1/50th of a second after the Big Bang. It basically, the entire universe would fit in the size of our Earth. One day after the Big Bang, it would have fit inside of our solar system. If you go far enough back, it would have fit inside a proton. If you go far enough back, it would have been able to fit in something even smaller than a proton, say in a quark or something like that. But anyways, that's the point. That's what the Big Bang is. And the Big Bang coming out of that point meant the space itself came out of that point, and the space continues to expand. And there is a different formula for redshift, or blue shift for that matter, the Doppler shift. There's a different formula that you use when you're dealing with the galaxy's redshift than you use for the galaxies being redshifted due to velocity. For instance, the redshift for the wavelength of light, for for a galaxy moving through space is the square root of c plus or minus v over the square root of c plus or minus v, where you choose the signs depending on which directions you're talking about. In this case, we just take the difference of the wavelengths divided by the laboratory wavelength, and that really is our redshift or our blue shift. That is because what we picture is light coming out coming out of something might have a wavelength this big, but as the universe expands, then this wavelength expands with it. So if the universe gets twice as large, then that wavelength will get twice as large. So that really is how this whole idea was thrust upon us. And what makes that cool is it also automatically solves the cosmological, or satisfies the cosmological principle, because every space is doing the same thing. Okay, every area of the universe sees exactly the same thing we do. So if you take, for instance, I like to do it on a balloon. Your book does a really good description there with putting paper clips on a rubber band. I highly suggest you do it. I would assign it as another lab if I hadn't given you so much work to do for the last lab. But you take a rubber band and you put maybe 6 or 7 paper clips on it after you cut the rubber band in half and pull it to, basically with no tension, but strong enough to hold up the individual paper clips. You put all of them equally spaced and you pretend you're the leftmost one, say A. And then you say, I measure the distance between each of those. Each one of those is maybe 1 centimeter, so that B is 1 centimeter away, C is 2 centimeters away, D is 3 centimeters away, E is 4 centimeters away. Now you stretch that rubber band until, say, the distance from A to B is 2 centimeters. Now you've got 2 centimeters from A to B, and lo and behold, B to C is another 2 centimeters. So the total distance between A and C is now not 2 centimeters, but 4 centimeters. And the distance to to D would not be 3 centimeters, but rather would be 6 centimeters. And if you did that same thing from E's perspective, you'd find exactly the same result. And that's the only way you can explain it, is by the universe itself doing the expanding, the universe being the rubber band, and the galaxies being the individual paper clips, because gravity locally is strong enough to overcome that expansion that the space is going through. The gravitational force, electromagnetic forces, those forces, the strong nuclear force, the weak nuclear force, all those forces that hold us and stars and galaxies together are strong enough to resist the stretching due to space. But within, or I should say, within a group of galaxies, or even a cluster of galaxies, the gravity is often strong enough to keep all those together as well. But then the center of mass of that galaxy would be moving along with space. But generally speaking, if you found lone galaxies, each of those would be obeying Hubble's law, which says if you double the distance away, you double the speed at which it's leaving you. And you got to remember that speed is not the galaxy traveling through space, but the galaxy being pinned to space and space expanding. So that's the really big weird thing about the Big Bang. If it doesn't make your brain hurt a little bit, you're probably not thinking enough about it. You probably don't understand it very well. It should make your brain hurt. It should be really mind-bending, because that's the only way we can understand the universe as it is. So let me go back to sharing the slides. We're right here. Now I've given you that intro to what the Big Bang is, and basically how we discovered it. And like I said, Hubble had discovered it, even though Ralph Alpher had predicted it also with Einstein's theory, as did George LeMaitre, and to some extent Alexander Friedman. So galaxy speeds are proportional to their distances. That's what we were saying. In fact, that gave us a Hubble law. So if you make a graph of receding velocity, in other words, the velocity at which things are moving away being on the vertical axis, and then you take the distance to those galaxies on the horizontal axis, then you'll get basically a straight diagonal line going up and to the right. The slope of that line is this h0, which we call Hubble's constant, which is about 70 kilometers per second per megaparsec. Remember, it's got to have units. The top units have to be the units of the y-axis. The bottom units have to be the units of the x-axis. So the top unit has to be velocity, and like I said, it's like 70 kilometers per second divided by megaparsecs. So that's really what the Hubble constant is. dg is the distance of the galaxy. Vr is the Hubble velocity, or excuse me, is the recession velocity. And then, of course, that graph gives us all of it. Here's the picture we were talking about with the actual paper clips. So if you put all these on there and you see, you imagine time going from here to here. So this is let's say 1,000 years ago. This is right now, and this is 1,000 years in the future. You could even say 1,000,000 years. So this is 1,000,000 years ago. This is right now, and this is 1,000,000 years in the future. From right now, we'd see this guy's 1 centimeter away, 2, 3, 4 centimeters away. Then after a time of 1,000,000 years, this guy is now 2 centimeters away. So its distance doubled. But this guy that was 2 centimeters away is now 4 centimeters away. So it doubled as well, and so on and so forth. That is really the idea of how to do the homogeneous expansion. This is one of those diagrams that come up in science books where you really need to read all the individual insets so you can make some sense out of it. So make sure you look that over. I gave you a rough estimate of it verbally, but the big chance is not only that A should behave like we see, but we'll also switch, say, to E, and it shows exactly the same behavior as A. So we feel like we're the center of the universe, but so does everybody else. That makes it consistent with the cosmological principle. So we learned in chapter, I think it was 18, on relativity and black holes. We learned first about special relativity. Then we learned how Einstein fixed the idea of gravity by saying gravity is not a force. Instead, matter tells space how to bend and warp, and then space tells matter how to move. So planets, stars, even humans and atoms and electrons cause little dimples in space, and those little dimples cause it to be not as easy to go in a straight line by it, just like it's not very easy to go in a straight line if you're really small walking on the surface of an apple, okay? Or walking on the surface of the earth, you're not really going in a straight line, you're following an arc because the earth is actually somewhat spherical. So it really is the space doing the expanding, and like I said, even the redshift formula shows that that's a different type of expansion than you're thinking of. It's not the galaxies moving with velocity, it's the universe itself expanding. So also you got to remember, when we look to distant objects, like when we look at our star, the sun, we're seeing it as it looked 8 minutes ago because light takes 8 minutes to get to us. When we look at Alpha Centauri, or the Alpha Centauri system, the light coming from that left it 4.3 years ago, and we're only seeing it now. So we're seeing the light as it existed 4.3 years ago, and that's called our look back time. And that's always something you're seeing. So by default, no matter what, the farther you look into the universe, the farther back in time you're looking. So for instance, if you're looking at 13 billion light years away, which is a huge distance, and it's right on the cusp of how far we can see, we're actually seeing the early universe then. We're seeing the universe as it existed 0.8 billion years after its birth. So that's something we always got to take into consideration. But it also helps us because we're seeing history unfolding. We're actually seeing the past right now. So that's kind of nice. So if you take the relative separation of the galaxies, you plot it vertically, and then you put it for certain galaxies, 13 or at the Big Bang, and then 12 billion years ago, and then 7 billion years ago, and then today, you see that the universe has expanded. These are just basically, this bottom line is like our galaxy, or the A paperclip, or later when we were doing it, it was the E paperclip. But the main thing is you see that as the distance away doubles, the relative separation of the galaxy doubled, which actually made the speed double. As it tripled, it made the speed triple, and so on and so forth. The galaxies will be farther apart in the future. Galaxies were closer together in the past. If expansion has been going on for a long time, then galaxies were once very close together. So if you actually look at this, you see following this back in time, all of these galaxies will eventually be at the same spot. That's, again, another idea that motivates us to think that the universe was created in an instant from an infinitesimally small thing. In other words, the universe was infinitesimally small. The Hubble time is the time when the separation was 0, and that's really just that slope that I told you, the 70 kilometers per second per megaparsec. That's 70 kilometers per second is a distance divided by time, and then you're dividing that by megaparsecs, which is another distance. So you see the Hubble constant actually has a unit of 1/time. So if you flip the Hubble constant over, you do 1 divided by h0 as they're showing here, and then you make all the units work out where they cancel out. Instead of megaparsecs and kilometers, you convert both the kilometers and megaparsecs to kilometers, or both the megaparsecs and kilometers to kilometers, or you just do them both to some common unit, meters, say. When you do that, then the meters will cancel out, and all you have left is a unit of time. If you convert that to billions of years, the 70 kilometers per second per megaparsec works out to be about 13.8 billion years. And that assumes that the Hubble constant was always the same and that the galaxy was always expanding at the same rate. When we do that, we find that the universe should be about 13.8 billion years old. However, we've later discovered that the universe is not expanding at the same rate. In fact, it seems to actually be speeding up. And George Smoot and the other person's name, who I forget, won the Nobel Prize for that discovery. So that's kind of a big deal. The Hubble time is the estimate of the universe. Its age is about 13.7, 13.8 billion years. At the time the Big Bang occurred, everywhere as an extremely dense point that began expanding. So that's another point. By me telling you the universe was created in a Big Bang, and including in the universe the space itself, when someone says, well, where did the Big Bang occur? You say right here, and you say right over there, and you say over there, and across the planet, and at the Alpha Centauri, and at the center of the Andromeda galaxy. Because remember, the universe was created in the Big Bang. Again, if it was that old idea of emptiness being here, and then the Big Bang created a explosion at a particular location, then you could trace all the velocities back to one location in space. And that's not the case at all. We don't see that at all. So really it is the Big Bang occurred everywhere because the Big Bang created the everywhere. Any questions on that? These are big concepts, so it certainly should be a little confusing to you guys. Any questions? So as Michio Kaku said, the Big Bang is a misnomer. It wasn't big, obviously, because initially it was the size of smaller than an atom. And it wasn't an explosion either. Wasn't a bang either, because in fact the vacuum of space basically doesn't carry matter, doesn't carry sound waves, therefore it would have been silent. Of course, the denser packed something is, it has the ability to carry sound waves. So maybe in that early segment, if you'd been here, you might would have been able to, if you had super special ears. But
So
yeah,
you could call it the little poof.
yeah, the little
I like that. I like that a lot.
the little like that one you slipped out when your boyfriend left the room or your girlfriend left the room. Oh, that's funny. Okay, yeah. So
I wasn't going to go that far.
well, I was, because that's me. That's what I do. All right. So the galaxies are not flying away from each other. Space itself is stretching or expanding. And what we use is a scale factor. So right now, if we sort of marked off in space every light year, okay, and then we come back a certain amount of time later, that you can actually calculate. I'm not worried about the calculation. I'm not trying to give you the exact figure. But if we come back sometime later and we find that those marks are now, instead of 1 light year, we measure them, they're actually 3 light years, then what we'd say is the relative scale factor from then to now is a factor of 3. Okay, that scale factor really is a measure of how much the universe has expanded since the Big Bang. If you're talking about relative to the Big Bang, if you're talking about relative to us, it'll be, Z is 1 right now, or excuse me, the scale factor right now, if we're talking relative to us, is a 1. But if we wait until everything we see, the distance between them doubles, then the scale factor would be 2. And then if we wait for everything that we see now that's 1 light year away is now 3 light years away, then the scale factor would be 3. And it turns out that scale factor is exactly related to the z that we use for the redshift. You remember the z being lambda minus lambda of the lab divided by lambda of the lab. That's the actual redshift. That's the z. Again, that's the one for the space expanding, not for relativity or things moving through space. So that z is actually related to the scale factor by 1 divided by 1 plus z. So if z equals 1, you clearly see that 1 plus 1 is 2, and then you have 1 over 2, that's 0.5, so the scale factor is 0.5. So that's the kind of thing we're using. So they're going to be talking about that and using that in this chapter and the next. So I just wanted you to understand that scale factor is another way we can talk about the expansion. And not only is it a way we can talk about expansion, it's a way we can talk about expansion from any point in time. We could say, what is the scale factor now since 1 day after the Big Bang? And I think that's on the order of 1,000, if I remember correctly. But we can also do it from, let's say, a billion years ago, in which case a billion years ago, you call the scale factor 1, and then you have a new scale factor that talks about what space is right now. Or we could call the scale factor right now 1, and we can talk about the universe later when the scale factor reaches 2. So that's what the scale factor is. And really is if you imagine these waves as being, let's say, 1 micrometer in wavelength. So from peak to peak is 1 micron. To next peak is 1 micron. To the next peak is 1 micron. Now, if the intervening period between now and then, so this is like right now, this is the future. If that time period passes by and now I find the peak to peak distance is 2 centimeters, then I know the scale factor is 2. And if I go and look at another point in time, and now the peak to peak wavelength is 3, I know the scale factor is 3. So that's really what we're talking about, the scale factor. And if you think about the light that was first emitted after the Big Bang, that's the background radiation. And I'll explain in a little bit where that came from. That light is being stretched by exactly that. So if right now the scale factor from the Big Bang is, say, 1,000, and I think, like I said, I think it is, then if the light came out as a single micron in wavelength, then you now expect that wavelength to be 1,000 times bigger, which would make it on the order of a millimeter. And that's exactly what we see, by the way. We do see, in fact, the background radiation, the microwave background radiation having a wavelength around a millimeter. It's like 1.2 or something like that. So the redshift of the galaxies are not due to Doppler shifts. Instead, the light is being stretched out as it travels through the expanding universe. This is known as the cosmological redshift. The more travel results in greater redshift. So when the Big Bang first occurs, we have all the matter and energy. And by the way, you really don't have, at a certain energy point, the things that make up matter that are actually made by smaller parts of matter, they have so much energy that those smaller parts can't come together. So you would expect, for instance, free quarks to float around in the early universe because we believe those are point particles. We expect electrons to be floating around in the early universe, but we do not expect protons because protons are made of quarks. Now, as that temperature resides, then you can get enough energy where the things are not going so fast that every time they collide, they break open a proton. At that point, then you get actual protons forming and maybe neutrons and stuff like that. And as it cools down more, you can maybe have those protons and neutrons and electrons grouping together to form atoms. And that's actually a critical time, by the way. Once you can actually find atoms forming, then the radiation is actually free to be released almost. And that's the radiation that we see from the microwave background radiation. So if all matter was in a small volume and conditions were very hot, you'd expect a Planck curve. So remember the Planck curve that he did those mathematical tricks to get a nice curve of intensity of radiation versus wavelength. The low wavelength then has a very, very sharp, steep curve. It reaches a peak. And that peak, of course, is inversely related to the temperature by Wien's law. Then from that peak, it gradually falls down way slower than this side did, than this side climbed. And you can find the temperature by, again, finding that wavelength. Well, we know at the initial instant of the Big Bang, that temperature was super, 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 super hot. And we can estimate it basically using the ideal gas law. And that's what Ralph Alpher did, using the ideal gas law, finding out what temperature it would be when the universe was, say, the size of an atom. And he would say, okay, at that time it's this temperature, or then at what temperature was it when matter started to come together in protons and neutrons and electrons to form actual atoms? That was called recombination, and that's the light we see from the microwave background radiation. It wasn't microwaves, well, actually in some sense it was literally microwaves because the wavelengths were microns, and that temperature happens to occur around 3,000 Kelvin. So this wavelength right here, if we say this was at the point of recombination, then at recombination, this temperature, if you plug it in, or this wavelength, if you plug it into Wien's law, would give you a temperature of 3000 Kelvin. At that point, the matter can't stop the radiation so easily. Before that, a free electron, a free quark, those things can absorb any energy whatsoever that comes out. So they're going to stop essentially all the radiation from coming out. But once these things group together, for instance, when quarks come together to make protons and neutrons, they only have certain energies that they're allowed to accept, just like when protons and neutrons make a nucleus with an electron orbiting it, there's only certain energies that the electrons can have. Therefore, it can only steal certain wavelengths. The same thing happens at the microscopic level as well, where there's energy levels for the quarks that have formed a proton, and its energy levels for the neutrons that have formed a proton. But in those cases, they're still not that free. So long as we have the free electrons, they can basically absorb any radiation whatsoever. So essentially all the light from the early universe is like it's enveloped in the radiative zone of our sun. Remember, the radiative zone of our sun, which is right outside the core of the sun is hot and dense, and it's putting out all this radiation. But the matter is so densely packed and so hot that it's free electrons and free protons and free neutrons. They can absorb any amount of energy. So it literally takes hundreds of thousands of years for the light to go from the outer edge of the core to the photosphere. That's what all of space is like until recombination. All the matter can absorb every bit of light and radiation that's created. Then when recombination occurs, you're very limited, or the individual atoms are very limited about what energy they can take. They can only take very specific wavelengths or frequencies. Therefore, all the other light comes out, and that's the light we're seeing. That is the microwave, now the microwave background radiation. But since that time, the universe has expanded about 1,000-fold. So the wavelength has increased by a factor of 1,000. So the wavelength that was 1 × 10⁶, which is a micron, is now 1 × 10⁻³ which is a millimeter, or it's actually more like 1.1, 1.2-ish millimeters. And that's what we're seeing now as the cosmic microwave background radiation. And it comes equally strong just about in every direction. Due to expansion, temperatures dropped. As thing expands, they actually do cool down. That's one of the ideal gas laws. The hot, dense gas had a black body spectrum like we thought. As the universe expanded, the light would redshift and the temperature would cool. The prediction, the resulting Planck spectrum would be uniformly redshifted by the expansion of the universe to a temperature between 5 and 50 Kelvin. I think we now estimate that temperature to be like 2.5 Kelvin, something like that. So pretty close. So that's what the temperature is. Again, that's just, it's sort of weird to say it that way, but it's really the temperature that Wien's law gives us for the heat. So that's what they're talking about, that 2.5 Kelvin or whatever. So the predicted spectrum was ultimately finally found. So here's the weird part. Like I said, Alexander Friedman and George LeMaitre predicted that the universe would be expanding. Gamow, on the other hand, I think he was working, I think he was at Princeton, Gamow was. You can fact check me on that because I'm not remembering exactly, but I think that's the case. But he was there with a grad student named Herman, and I think his first name was Robert, maybe. And he was also there with another grad student by the name of Ralph Alpher. And Alpher just died in 2007, which is a bummer. But he was at Union College, the same college up in New York or New Jersey. I think it's New Jersey, that Barbara Streisand attended. But anyways, he was working with George Gamow, and Gamow is the guy that wrote all the cool little books on relativity and quantum mechanics about like Mr. Tompkins and all this, trying to relate it to the masses, and did really a good job. But he was a really good idea man, but he didn't have that strong mathematical skills. So he gave his graduate students, Alpher and Herman, a project, and their project was to work on this idea. Well, Ralph Alpher did basically the lion's share. Herman did do some important contributions, but he wasn't on the main paper that did the most. But basically what he predicted was that the universe would have a very specific temperature at the Big Bang. and that right now that temperature would have dropped down to like 2.5 Kelvin. As you see now, it's 2.73. And that we should see radiation coming from every direction. He also predicted what elements would be come out of the Big Bang, and he predicted in what percentages. He used the percentages that we knew of for hydrogen and helium to set up his scaling, if you will, and then that gave us estimates of all the other matter, and he was right on the money with that as well. The sad part was Ralph Alpher was sort of ripped off by history. And here's a story that's interesting about physics, but it's also kind of sad. But your book doesn't talk about it. I got it from Simon Singh's The Big Bang. That's a really good book. Simon Singh's a fairly famous person for being sued by the British Chiropractic Agency or Union or whatever it was. But he's a particle physicist, a bright guy. He's written several books. He wrote The Mathematics of the Simpsons, which is excellent. I highly recommend. But The Big Bang is really good. So there's this problem in that Gamow is a bit of a huckster. Everybody thinks of Gamow as this funny guy, but he's also brilliant. Everybody knows he's a brilliant man, and he has really brilliant ideas. He's a good physicist. He's not that good, like I said, mathematically, to do a lot of the hard mathematical calculations, but he's still a really good physicist. And he has this intuition where if you do a calculation and you get this answer, he'll look at it and say, that can't be right. And then you find out that you made a mistake. So that's the kind of physicist he was. But everybody also knew him as the funny guy that's always playing practical jokes, not unlike Richard Feynman, with hiding stuff in people's desks and stuff like that, and stealing stuff and just being funny. So he had this paper, and it was going to be Alpher and Gamow, which sounds a lot like alpha and gamma, right? So he said, well, I can't let a paper go out for publication with Alpher and Gamow and not have a beta, because it's clearly got to be alpha, beta, gamma paper, right? So he asked a guy by the name of Hans Bethe, who many people actually did refer to as beta in some sense. But anyways, his name looks like a beta as well. So he asked him to be on this paper, and Hans Bethe, who also ultimately wins a Nobel Prize, Hans Bethe's like, I can't do this. It's like stealing work from your students. He said, no, they're cool with it. They think it's hilarious. It'll be great. And he said, okay. So he puts his name on it. Well, it gets published as the alpha, beta, gamma paper, which should be monumental. It should be this nomenclature that everybody uses, just like everybody calls the book Gravitation MTW, or the Bible of Gravity. There should be this reference all the time of the alpha, beta, gamma paper, because all these huge predictions they made. Well, people read it and say, oh, it's another one of Gamow's jokes, alpha, beta, gamma. So nobody read about it really. A decade later, the group, maybe that was the group at Princeton. Yeah, I think that was the group at Princeton. They later went to Berkeley, but I think they were at Princeton. So wherever Gamow was, I don't know. But this other group was working under Robert Dickey. They were working on this group. They did the same calculations and got the same result for Ralph Alpher. They didn't have any idea that Ralph Alpher had done it, just because they hadn't read the papers or whatever, because they thought it was a joke. As it happens to be, they built a device used to detect microwave background radiation. It was very small. It was called the Dickey radiometer. And they tried to look for this radiation signal, and they just couldn't find it. But it was technologically at the university level, they didn't have much money to spend on such a thing that they needed. What did was the private sector. And in fact, I think they were working for GE. Or no, I think they were working for Bell Labs. Bell Labs had a very, very fiduciary reason to be sinking money into this type of detector. Specifically, they had a microwave detector in New Jersey, and they were trying to create what is now cellular service and all that stuff. So they had Bob Wilson and Arno Penzias working at this laboratory, and they were having problems trying to pick up signals and stuff like that. They kept getting this background radiation that came from every direction. They thought it was something wrong with their equipment. They cleaned it out, all that stuff. Just couldn't get it to work. Finally, they heard about the Dickey paper, and they realized, hey, I think we were the ones that found the thing that they're looking for. So they published it in an astronomy journal. They won the Nobel Prize. Not Ralph Alpher, who, by the way, predicted it correctly a decade before the other people that predicted it correctly, and not the people that predicted it correctly a decade later. They didn't win the Nobel Prize, but in fact, Bob Wilson and Arno Penzias did win the Nobel Prize for discovering the microwave background radiation in that little tower in New Jersey, which you can see, by the way. I think the photograph of Penzias and Wilson in your textbook I wanted to say that photograph was them in front of their microwave detector, but I can't be sure. But you definitely saw it in the Beyond the Big Bang video that we showed at the beginning of the semester. So that's sort of the background story. It's kind of a bummer, though, right? You know, Ralph Alpher, he did some kick butt work, and he really should have heaps of accolades heaped on him or whatever, but he doesn't. So here we are. So let me go back to sharing the screen so we can finish off these slides. So as we said, the universe was expanding. We made predictions. Yeah, that is it. That's the antenna right behind it. There's Arno, and this is Arno Penzias, and this is Bob Wilson, both of which are still alive. I wanted to say that Arno Penzias might have recently died, but I'm not sure about that. But they're Nobel Prize winners. They both won a Nobel Prize for finding this. That's their radiation, their microwave antenna, if you will. They found it in 1965. As I said, they won the Nobel Prize. It turned out to be a Planck spectrum with a temperature of 2.73 Kelvin. The peak is in the microwave, therefore we call it the microwave background radiation instead of just the background radiation. So it's the MBR. It's the same in all directions. Basically, when you look in any direction, you're always going to get the same signal. That was what was kind of confusing to them, but also that was what told them that it wasn't ultimately reasonable to think of it as computer error because it comes with slight variations from every direction. The cosmic microwave background radiation really is the time of recombination. So these pictures, you can read the description that your book uses to talk about recombination, but this is sort of an recombination, and this is post-recombination. So basically what happens is the universe is packed full of free particles. And those free particles, since they're free, can't really be restricted to certain wavelengths. They can absorb everything. So for instance, if electrons flying around and a 1,224 or 1,224 joule photon hits it, it absorbs the whole thing. If a 1,232 joule photon hits it, it's going to absorb that. If one of 1,243.8 hits it, it's going to absorb it. So basically, all the radiation that's being emitted can be absorbed because they're not limited to just taking certain accepted radiations like they're in a Bohr orbit. And because of that, all the radiation prior to recombination can't be seen. But the instant recombination occurs, which is around that critical temperature of 3,000 Kelvin, then the atoms are actually in atomic form and can only accept wavelengths and energies that match the energy differences between the, say, the electron levels. When that happens, all the other radiation escapes. And at one instant, you get a huge amount of radiation coming from the universe in every direction. And that's what we're measuring. But since that has happened, the universe has had a scale factor on the order of 1,000. So that wavelength, which I said, which was 10 to the negative 6 meters or 1 micron, has now been increased by a factor of 1,000. So it's 10 to the negative third, or about 1.2 times 10 to the negative third meters, which is 1.2 millimeters. That's what we're seeing now. At that time, light was no longer blocked from its travel by all the matter, meaning at the time of recombination, the light could travel freely and cooled by a factor of about 1,000 to about 2.73 Kelvin, and as confirmed by satellites. So another prediction of all this, and this is something that Ralph Alpher did as well, is he worked out the nuclear physics. And oddly enough, so did Fred Hoyle that they talked about in the video. Fred Hoyle worked out the nuclear physics and even got a Nobel Prize for a guy by the name of Fowler at UC Berkeley, basically by telling him, hey, I believe there's a state of carbon that no one's ever seen before, this carbon nucleus that no one's ever seen before, specifically because I need it to make sense of nuclear synthesis. In other words, he was using what we call the anthropic principle. Basically, the anthropic principle says the universe, is very special. And if, small little things like the epsilon zero from Coulomb's law or the G from Newton's law of gravity, all those different things, all those constants weren't pretty precisely what they are now, humans could not exist, life could not exist. The anthropic principle turns that on its head and says anything that had to have happened must have happened, or else we wouldn't have humans. So he used that anthropic principle to say, hey, I don't think we can get we can get elements beyond hydrogen, helium, a little bit of lithium, boron, and beryllium from the Big Bang. This is what Fred Hoyle says, unless this isotope of carbon exists. And he used that idea and predicted that carbon existed. And then if that was the case, then he could understand how all the other elements came from nucleosynthesis, i.e. that stuff we learned about high mass stars. So he went to Fowler, who's this physicist at Berkeley, experimentalist, and asked him to look for this. And he's like, I got enough things on my plate. Why do you give me this? He said, well, if you find it, you'll win the Nobel Prize. He's like, okay. So he stopped everything and looked for Fred Hoyle's special carbon. And he did end up finding it and did end up winning the Nobel Prize. And that allowed Fred Hoyle to introduce us to the idea of the Big Bang nucleosynthesis, part of which Alpher had worked out. Well, Alpher had just worked out basically that we'd have mostly hydrogen and helium and what percentages. And he said that there might be some lithium, and I think he might even said beryllium would be there, but not, I don't think it was boron. We've since discovered boron should be in there. But Hoyle takes this and runs with it to find that basically the lights of stars produce the other elements, which is critically necessary. So before recombination, everything would have been much hotter and more dense. At high densities, nuclear reactions occur. This process is called the Big Bang nucleosynthesis. So this is, again, high energy, not unlike the energy under a supernova explosion. The energies are so high that they're like that, so they can create those other elements as well. Fusion in the early universe produced mainly hydrogen and helium. Prediction, 24% of matter should be helium. No star has been observed with helium fraction of less than 24%, so that's completely consistent with that. And that ultimately led us to the modern idea of the Big Bang. It, again, not thrust upon us from hell or Satan, as Louis Gohmert would said, but thrust upon us by, in one case, even a Jesuit priest who saw that this was just the nature of the theory that defines the universe, i.e. Einstein's general theory of relativity, and also as the experimentalist that was Edwin Hubble discovered in 1929. All this stuff forced us to the conclusion that the universe was created in a monumental Big Bang, which again might be called the small or okay. If that's the case, then that really is an amazing achievement. And as best we can tell, it is the case. It's a full robust theory at this point. It's no longer a hypothesis. And we now use, you can see in this process of science, that sort of triangle missing a leg. That's the uppercase lambda. For some reason, I was thinking gamma for a second. That's the uppercase lambda. And that is the cosmological constant that Einstein introduced to his equation of general relativity to make the universe static. Now we use it as a gauge of how not static it is. So we actually use that in physics. Even though Einstein introduced it to do one thing, we use it now to introduce ideas like is dark energy causing the universe to expand more rapidly and stuff like that. So here's that calculation where they can show that 70 kilometers per second per megaparsec gives you a time of 1.4 times 10 to the 10th years. You can see that in the working it out examples. Here's the working it out example with the scale factor. That's basically it. So we were able to finish chapter 21 in this one seating. So I'm not going to need you guys to come to lab. I'm giving you, again, the lab time this week to complete your observations of the constellations I gave you. Remember those new constellations I gave you? I think it was Ursa Major, Perseus, Cygnus, Orion, Virgo, and either Sagittarius or Scorpius. I can't remember, but I gave you like 7 constellations for you to research, find out all the constellations bordering it, try to find it in the night sky. By the way, the Cygnus and Lyra and Altair, Aquila, are all part of the summer triangle. So you're not going to see those until either early in the morning or very, very, very late after midnight. So you probably won't be able to see anything from that summer triangle until those hours. But other than that, you should be able to check out everything. Does anyone have any questions about any past material today or anything else? Is Kimberly about to fall asleep? Are you rubbing your eyes for that?
I had a question, Professor.
Oh yeah, go for it.
I wanted to know about the what was your expected word count for the movie write-up for us to receive the full 200 credits?
If you just do the minimum, which is, I think I said 15 observations, and those observations have to include a drawing of the actual image of the sun, or a photograph would be acceptable, but a drawing would be easier. But what I need is not only to see whether it's a crescent or a gibbous or half or full or whatever, I need to see exactly what the orientation is. So, I don't want everybody's crescent moon to always be like this. In some cases, when you look at a crescent moon, it'll be like this. Others, it'll be like that. Others, it'll be like that. Others, it'll be like that. All sorts of stuff. So I need that. I need you to tell me what location you were in. Just a city would be fine. I need you to tell me what time of day it happened on and what date it happened on, as long as, and whether it was high in the sky or low in the sky. Also, what direction of the sky you were looking. So were you looking east or south or west or northwest or whatever, and literally. East, south, west, southwest, those are more than enough. If you do more, you can get even more astro points. So basically just doing that bare minimum, I think gets you 100 astro points flat. If you do a lot of bells and whistles, maybe use your phone as an inclinometer to tell the angle at which the moon is up in the sky, and maybe you use your compass of your phone to tell you what direction you're looking in to the nearest degree. All those things would give you more points and make you get more than 100.
I was speaking about the movie write-up.
Oh, you said the movie. I'm sorry. I thought you said moon. And which movie were you referring to?
I was doing one on the lab. I can't remember what the lab was called, but it was a lab movie write-up.
Oh,
We
that
had
was the history of the Earth one, probably.
Yeah, the history of the Earth.
Yeah, so that one, I have a bunch of questions you have to answer. And normally you just do a write-up of any movie, and as long as you do the 200 words or whatever I say in my syllabus, you'll get the astro points for it. But in this one, I actually made up very specific questions that you have to answer. And they're posted, so you need to do those.
And we can still, yeah, I did the questions for the lab, but we can still do a write-up on it.
On the movie, yes, you can just do a whole separate write-up on the movie itself, and just like I said, do that's sort of double dipping, but I don't mind with regards to movies, especially that one, because I made you go in depth to answer those questions.
Right.
Okay. And there's other movies you can do too. Interstellar, I think, was one. Mars was another one. Was Mars the one with Matthew? No, not Matthew. Was it Matthew?
Matt
the
Damon.
guy who went to Mars and got trapped. What was that movie?
Martian.
Yeah, it's The Martian. That's what it is. Thank you. Yeah, you can do one on that one. That's a great one. Was Interstellar the one with Matthew McConaughey and the black hole and all that cool stuff?
Yeah.
Okay, so that's another good one you can do. Contact is one you can do. That's not only a book by Carl Sagan, but it was a movie made based on the book. The Cosmos series, you can do those. All those are some really good. The original Cosmos, you can do each of the episodes, as well as the new Cosmos from a couple years ago, as well as the newest Cosmos, which is out now as well. So you could, I set up the 1,400 points for Cosmos. So that still stands, but you might want to focus on, say, the first and the last, or, just choose episodes and get 100 points for each one. It's your responsibility to find them, though, and some libraries have them, so you don't have to actually go out and buy it. I bought them myself because I'm a nerd and like to watch these things over and over again.
We can also do the crash course videos on YouTube, right?
I don't think you can do a write-up for those because they're so short. It'd be hard to write 200 words on a 10 to 15-minute video. But I put them up there just to help you understand the material. If you want to do something bigger and write a paper on, say, general relativity or black holes, and you use those as some of your sources, that would be fine, but not generally just write up a video on the crash course because they're just too short. Okay. Yeah, I'm all about you guys doing independent research on something that's interesting you. I want you to follow your curiosity, because sometimes the curiosity and the awestruck moment is what turns a business major into a science major, which we need a lot more scientists and less businessmen, in my personal opinion. Not that businessmen don't help our economy and stuff.
Professor?
Yes.
I don't have a question, but I was wondering if you could, after class, just take a look at the email I'd sent you a few days ago.
Yeah, Madison. Yeah, I don't even remember seeing that one. But I've actually been occupied doing a bunch of stuff since Thursday, so that might have been it. But yeah, I will check it out. Do you want to wait till it's over and I talk to you about it, or you just want me to reply to you right after class?
You can just respond through email. That's fine.
Okay, we'll do. Sorry for missing it, Madison.
Oh, that's all right.
Anybody else have anything? Because everybody's free to go. If not, remember, no lab, everybody.
Okay, yes, Professor. Just before I leave, I have one last question.
Go for it, Money.
I was doing multiple write-ups for my astro points because I know that we have to get a certain amount, which is over
Right.
1,500. And I just wanted to know, did you want us to turn them in the in the movie in module, or did you want us to do it in the lecture video write-up module?
If it was something we did for lab, you have to turn it in at both places. If so, you have to turn in one for the lab itself, and then one for astro points in the lecture portion.
There was a write-up for lab.
Yeah, it was a write-up for. It was actually a lab experiment. That's why I gave you the questions and stuff like that. So there's a turn-in section for it in the lab course. You should turn it in there to count as your lab credit. But then you go to your lecture course and you can turn it in there as well. I don't remember if I put a separate link on I want to say it's week 11 or week 12, something like that. It might even be 13. I don't know. I think I might have put another link there. You can put it there and that'll get you your astro points. If not, look in the astro points turn-in area. There's should be a link there for you to put it to.
Okay. Do you know the name of the lab off the top of your head or no?
I think it's History of the Earth. Let me look real quick though while I'm here, because that's easy enough.
I actually left a note because I know that you have some people that are in your lab that aren't in your class. I
Right.
turned mine in with theirs. So do you want me to turn around and turn it in the
Yeah,
lecture?
do both or you won't get both sets of credit.
Okay.
I'm
I can
pulling
do
open the lab right now for our course so I can find out what that lab was. So it wasn't week 13. Oh, here it is. Lab Making of a Planet. That's it. Because I thought the movie was called History of the Earth, but it wasn't. It was called The Making of a Planet. So it's week 11, and you turn it in as History of Earth Questions.
Right. And
Okay.
I turned that in the lecture video right up.
Yes, you turn that in lecture. That's where I found it in lab was week 11. So if you look in the lecture, you might find it in week 11 as well. I'm checking that right now. I should have did that first. Would have saved time.
Okay. Oh no, you're fine. I wrote it down, so I'm pretty sure it was week 11.
Yeah, whenever I give double credit, let something count twice, I'm going to expect you to turn it in double. So that'll, I don't know why I'm telling you these general rules, so late in the semester, but here we are. Yeah, I'm looking at the modules right now. I'm trying to see week 11.
It's there.
It is there?
It is.
Yeah, I'm about to say it's already its own thing, but the module that I'm talking about is called lecture video write-up module. You know what I'm talking about?
Yeah, it's up in the astro points area, or the astro point turn-in area. Yeah, so this one I did call Earth Making a Planet for astro points. That's in week 11. But yeah, what Amani's talking about is the section is called astro points turned in here. So you can turn in things there, but what happens if you turn in something like that you already got credit for somewhere else? In fact, I actually had it listed as a link, and I just I made it no longer available to you guys. But if you turn it in there, so attempt to get 3, you won't get any more points for it. So don't waste your time putting it in there. But yeah, extra lecture video write-ups, that would just be any videos I showed in lecture or any videos I mentioned in lecture for you to watch. That's like every now and then I'll just come in and say, hey, I found this cool YouTube video. I want you guys to watch it. That's what that is. I don't recall doing any of those yet. So there shouldn't be anything in that. Okay.
So the ones that we have done, we turn it in the movie in module.
Yep.
Okay. All right.
That it, Amani?
That's it.
All right. Have a good one.
All right. You too. Take care.
Autumn, do you have anything, hon?
Yeah, I need your help.
What's up?
You're stop recording. Okay, yeah, I can.
Oh,
I'm having
let me
control.
kill that. Hold on a second.